So let's consider how we fill and remove electrons from our orbitals. So let's have a recap and look first of all at the orbitals available for period 4 atoms. So period 4 means we just go up to krypton, and those are the orbitals we have. So krypton, all of those would be full. So let's try putting some of our electrons into those orbitals. And the first one we're going to do is going to be lithium. So lithium, 3 electrons, so we're going to put 1s, it's going to have 2 electrons, and then 1 electron in the 2s orbital. Give me my 3 electrons. Let's move along now and do nitrogen. Nitrogen's got going to have a bumper 7 electrons, so we fill up that 2s as well, and then we individually occupy each 2p orbital as well. So they first of all go into separate orbitals before they pair up. Magnesium now. So we're now into the 3rd shell, and we're using the 3s subshell. Over we go to chlorine, and now we're up to 3p5. And let's go into some transition metals now. Vanadium. So vanadium, you notice we've got the 4s filled first before the 3d. We've got 3d3 there, and one more just for fun, nickel. We're now up to 3d8. And of course, if we got to zinc, we would then be up to 3d10, and we'd then be moving into the 4p subshell. Oh, I tell a lie. We've got one more, germanium. So let's use that 4p. And you can see germanium's the second one into the 4p, so it's going to be 4p2. So that's quite a lot to write out for germanium. We're going to try and shorten it. And the way we shorten it is we can replace some of the electron configuration with a noble gas. So let's look at argon. Argon has that electronic configuration, and you can see that that matches up with germanium like so. So we're going to replace that with argon, and then we just fill out the rest that germanium has in addition to argon's electron. Key thing is you can only use a noble gas for that one. So now let's look at how we form ions. So let's go back to magnesium. And we're now going to form the Mg2+ ion. So we're going to lose 2 electrons, and we know they're going to go from that 3s subshell, so that we will end up with neon's electronic configuration. Let's move on now to chlorine. We're going to form the chloride ion there. So we're going to gain 1 electron to give us 3p6. Right, so now let's look at some transition metals, vanadium. So that was vanadium's electronic configuration. We're going to form the vanadium 3+ ion. Now, key thing to remember is that we lose the 4s before the 3d. I know it seems bonkers because we filled it first before the 3d, but we're also going to lose from the 4s as well. So the electronic configuration of V3+ actually ends in 3d2. The 4s electrons have gone. They're the first ones to be taken away from the atom. So just remember, 4s loses electron before our 3d subshell. Now a couple of odd ones to remember, chromium and copper. So chromium has that electronic configuration. You'd expect it to be 4s2, 3d4. However, chromium likes to be a little bit different and likes half-filled subshells. So it's a half-filled 4s and a half-filled 3d. Right, so how can we use a periodic table to help us work these out? So let's go back to our old friend, the periodic table. We find out for all those in the highlighted in red, the highest energy electron is in the S subshell, and therefore they are all called the S block. Now let's look at nitrogen, chlorine, and germanium. You notice they all end our highest electron is in the 2p subshell. So strangely enough, all of those block are called the P block. And you guessed it, vanadium and nickel, they end in D. So those in the middle are the D block, and if we were so excited we wanted to, we could go and look at the F block as well, and we'd find they were in the F subshell. So that's how we divide the periodic table up into the 4 different blocks. How can we use that? Well, you notice down the left hand side I have got the numbers 1 to 7. Those are the period numbers as we go across, and we're going to combine those with the blocks to work out arsenic's electronic configuration. So key thing is for the S and the P blocks, you can see that all of those are the period numbers relate to the shell that they're in. So for example, when I look at nitrogen over here, nitrogen is in period 2, so its outermost electrons are in the 2p subshell. Key thing is the D block, we go out of sync because of course these are the 4s, and then we have the 3D here. So just remember that the D, we have the 3D, then the 4D, and so on. So let's say we're going to work out the electronic configuration of arsenic now. So there's arsenic, and we know that, we've worked it out. How could we have done that in a slightly faster way? Well, we could have looked and we could have said, right, okay, we've got a 4 there, and we know it's in the P, and we've got 1, 2, 3 in, so we're going to have 4p3, and we know this is up to 3D, so this has all got to be the 3D field there. So you can kind of work out where you are straight away. You kind of think, okay, I'm on the 3D here, got up to zinc, so I'm up to 3D10, and this is going to be the 4p, and then I've got 3 in, 4p3. Like, we're now going to look at how we can work out how many orbitals are occupied. This is quite a common question at A level. It should be quite fast, but it can be a bit tedious to draw all those little lines out and fill your electrons in the boxes. So let's have a think about that. So we've got to zinc. Zinc's got 30 electrons, and we know that they must all be paired in orbitals because I finished filling my D subshell. So if I got 30 electrons, 2 electrons per orbital, that means I'm going to have 15 orbitals. And then I only need to worry about the other 3. So I've got 3 in the P subshell, so they're all going to go into 1 each. So I'm going to have another 3 orbitals for them. So I'm going to have a total of 18 occupied orbitals. Let's do one more, just for fun. Ruthenium. So, oh, that looks a little bit like, oh, imagine you had that, drawing out all those boxes. Well, it's quite easy. We can go up to 5s2. That's a shortened electronic configuration. And if we now go to the end of 5s2, which is strontium, we see that strontium has 38 electrons. So 38 electrons divided by 2, that means I've got 19 field orbitals. Now I only have to worry about the D block there. So ruthenium has 6 electrons in there. So those 6 electrons, first of all, they'll all go 1 each, and then one's going to pair up. But basically, they're all going to have an electron in. So I'm going to have 5 occupied d orbitals, and therefore in total I am going to have 24 occupied orbitals. So that's it. Hopefully that was a little bit helpful. How we fill the electrons in, how we form ions, and how we can use the periodic table.